Our first talk is going to be multiband parameter estimation with phase coherence and extrinsic marginalization, extracting more information from low-SNR CBC signals in LISA data by Shichao Wu.
Okay, hello everyone. I'm Shichao Wu, a postdoc from AI Hanover. So firstly, I want to thank for the organizers to give me this opportunity. Today, I'm going to talk about the multiband parameter estimation with phase coherence and the extrinsic marginalization. So my today's talk is based on this paper on arXiv. In this paper, we implement a novel coherent multiband analysis method into the PySBC data analysis pipeline. And in case of you don't know, PySBC is a magic fusion-based pipeline, which initially designed for the LIGO data analysis. And it was used to make the 5 sigma significance plot for the very first gravitational event. And nowadays, LVK collaboration is routinely use our pipeline to find new CBC signals. For example, here is a screenshot from the latest JWST5 paper. As you can see, the majority of the newly found CBC sources are firstly detected by our PySBC pipeline. And in the literature, PySBC is already heavily used for the studies for the next generation ground-based detectors data analysis, for example, Einstein telescope and Cosmic Explorer. And in the past few years, we are trying to extending our PySBC pipeline to do spaceborne detectors data analysis, and also some other spaceborne concepts. So in the next decade, we will have Cosmic Explorer in US and the Einstein telescope in Europe. In the space, we will have LISA. So the question is, can we utilize all of them to do some interesting science? Here are the very early concepts for the multiband observation. For example, the most famous one from Albert Sasana. He shows that the stellar mass black hole binaries will firstly show up in the LISA frequency band. And after many years of evolution, they will finally get merged in the ground-based frequency band. And similarly, Paul also showed that the intermediate mass black hole binaries are also good candidates for the multiband observation, with much shorter waiting time between LISA observation and ground-based observation due to their heavier mass. So as data analysts, we really want to infer the source properties, which means we need some kind of parameter estimation techniques. So up to now, more than 95% of the multiband paper relies on a technique called the facial information metric. It relies on the linear signal approximation, which requires the highest of the signal and the known injected parameters. Instead, 4 years ago, Alessandro Tubiana proposed that we can do the archival multiband Bayesian parameter estimation. That is, use the 3G ground-based detectors posterior of the LISA prior. Without external information from the ground-based detectors, you will just get the very noisy posterior from the LISA data, which shown in the green. So there are so many local maximums on the likelihood surface, and also the posteriors. And they found that the archival multiband inference method has a limitation on the SNR threshold. Their method requires the signal SNR to be higher than SNR5 in this LISA band. But unfortunately, the majority of the signals, for example, for the JWST3-like events, they will below that SNR threshold. So even for the LISA consortium, they don't expect that we can do much science for the stellar mass black hole binaries with a fiducial 4 years observation and a conservative LISA SNR threshold, which is 8 here. So in my study, I generated the multiband MOG data based on the JWST3 population models. For example, use the population posteriors to draw the samples. And for the network settings, I'm using LISA and the xylophone configuration of Einstein telescope and also 2 Cosmic Explorer. And I'm assuming several different LISA mission durations and with a 75% of duty cycle. So this slide summarizes the expected multiband event rates and also their corresponding SNR distributions in my simulation. So on the left-hand side, I show the results for the 2 different LISA mission durations. For example, the 4 years and the 10 years multiplied by the 75% duty cycle, and the 3 different LISA SNR threshold, 3, 5, and 8. So overall, you can see that if people have a data analysis method can analyze Lisa SNR down to Lisa SNR3 rather than SNR5, we can almost double the number of multiband events. And on the right-hand side, I show the SNR distribution for those multiband signals. For example, the late in spiral merge and rundown part of those multiband signal in the 3G network will be around 500 SNR. But unfortunately, the more than half of the multiband signal, they are very early in spiral part in the Lisa band, well, has a Lisa SNR below SNR5. So here I show a more realistic multiband plots comparing to the previous very early concepts. Because this one used the second generation time-linear interferometry and also based on a more realistic population model. So you can see that within the Lisa mission lifetime, the majority of the stellar mass black hole binaries will start from the 10 to the minus 2 Hertz, which is higher than the frequencies affected by the galactic white dwarf binaries. So in order to achieve the fully coherent analysis for the multiband observation, there are two major difficulties needed to overcome. The first one is due to the different conventions, the geocentric frame is usually used for the ground-based data analysis, and the solar system barycenter frame or the Lisa frame is usually used for the Lisa data analysis. So even for the same signal, they will have different sky localization, different signal arrival time, and also different polarization angles in those frames. So they are in the different parameter space. And the second biggest challenges is that there are so many local maximums. For example, here I show a SNR5 signal in the TDI A channel as an example. So you can see that in the time domain, the overall amplitude of the signal is almost 4,000 times weaker than the instrumental noise. And if we just use the exact same waveform as a template to do match filtering, we will get the very noisy SNR time series. And mathematically, we can prove that the match filtering SNR used in the signal detection is equivalent to the log likelihood ratio used in the Bayesian parameter estimation. So this also means there are so many local maximums on the likelihood surface. So in order to overcome the first challenges, first time we introduced the multiband joint likelihood ratio calculation during the sampling, which utilized the rotation matrix to unify the parameter space. Basically, we can transform the Lisa signal from the SSB frame or the Lisa frame into the geocentric frame to be sampled with the ground-based detector during the sampling. And in order to reduce the complexity and the dimensionality of the parameter space, we utilize the importance sampling to marginalize over those extrinsic parameters. For example, for the aligned spin quasi-circular ones, we can reduce the parameter space from 11 dimension to just 4 dimension. So the sampler only needed to sample the 2 component mass and the 2 aligned spins. And after that, we can use the intrinsic posteriors and the corresponding importance weights to fully reconstruct the marginalized extrinsic parameters. Here I show an example of the high mass stellar mass black hole binaries. For example, its corresponding SNR in the Lisa band is around 3, and the late in spiral part and the merger rundown part in the 3G network is around 500. By including the Lisa SNR, the overall multiband SNR is only increased by the 0.01. Here I show the 1-year observation of the time domain signal. So you can see that it's almost a standard source signal with millions of waveform cycles, but modulated by the Lisa orbital motion. And it's almost negligible compared to the instrumental noise. But if we use our coherent multiband method, we can robustly recover the true injected parameters. Because in the code implementation, we extended the heterodyne likelihood into the joint multiband likelihood case. So for the first time, we can carry out the multiband Bayesian parameter estimation efficiently on the population scale. So here I use 2 histograms to summarize the population results. For example, here I show the distribution for the Ys of the 90% credible interval for each multiband posteriors, for the detected frame trim mass, and also the mass ratio. And the vertical axis here shows the average number of the multiband signal, which has a low-SNR higher than 3 in each precision beam. And the different color means different LISA observation time. For example, the blue one shows the just 1 year LISA observation. And as a comparison, I also show the measurement results, the accuracy of that for the ground-based detectors with 7.5 years observation in the gray. So overall, you can see that even if LISA will just observe 1 year, the detector trim mass, the 90% credible interval, is still better than the golden events that will be measured in the 3G network in almost a decade. So here are the take-home messages. So by utilizing the coherent multiband analysis, we can almost double the number of useful multiband events. Yeah. Thank you so much.
All right, we have about 4 minutes for questions. Are there any in the room? If so, please come up to the mic.
Cool stuff. Just a question on the on your LISA analysis there. What method are you using to model the LISA response? Because it can get expensive up at those high frequencies, right?
Yeah.
Folding in. So I'm just curious what you're doing to handle that.
Yeah. For this study, I use the BBFX waveform package. So the code developed by Michael Kaz. Yeah, and basically it's a TDI modulated IMF norm D waveform. Yeah.
All right, I'll check. I'll check on the implementation there. Okay, thanks.
Thanks.
Other questions for the room? I'll take chair's prerogative. So what do you see as the most interesting science that you can get out of this kind of joint constraint?
Yeah, for example, at the moment, in the LISA consortium, I'm working with, also collaborating with Ricardo and Astrophysical in the Astrophysical working group. We want to use this method to regularly check the updated LVK population distribution, to update the expectation for the LISA observation, and maybe also extend it to test from astrophysical formation channels, for example, AGN disk. And also, the most important thing is that the multiband observation can put a very constrained limit for the testing GR things. Yeah.
Cool, thank you. Do you have any online?
No.
All right.
Okay.
Last chance. All right, let's thank our speaker one more time. All right, our next speaker is Casey McGrath, who will talk to us about multi-messenger exoplanets with LISA.
All right, thank you so much. Yeah, I am excited to have the opportunity here to be able to chat about a project that I've been really interested in working on and sharing here on behalf of the colleagues also listed on this first slide about the possibility that if we can potentially detect exoplanets around some of the LISA sources, the double white dwarfs, then these could possibly become multi-messenger exoplanets if we can also observe them using electromagnetic techniques. So I will start off by just saying, at the moment I can't point you to anything directly. We have 2 papers that are currently undergoing peer review, so if you are interested in this, absolutely welcome to reach out and chat with me this week or afterwards, and keep an eye out in the near future. Hopefully those will be coming out pretty soon. Okay, so to date, we have detected and discovered over 6,000 exoplanets using a number of different techniques, many of which you can see listed here. But one of the most prolific methods of all of these has been the so-called radial velocity method. The idea there being that if you have a star with a planet orbiting around it, then the star will wobble due to the gravitational interaction as it moves around that common center of mass. And this will induce a Doppler shifting on the observed spectral features from that star. giving us the indication that there's a planet in the system. More recently, since around like the late 2000s or so, individuals have started asking the question, what if, though, we replace this star with something that's emitting gravitational waves? Still with an exoplanet, would you get some kind of radial velocity-like effect, but now in the gravitational wave spectrum? And while certainly there are a lot of similarities between these two techniques, there are also some really interesting and critical differences, which is why I think it makes this fun. And let's just think of this in context of the LISA case. So the most abundant source that we're going to detect are the double white dwarfs. And we know those particular systems are emitting a very nearly constant frequency gravitational wave, which is already very different from the electromagnetic picture where the star is emitting a nearly continuous spectrum with just missing discrete spectral features. So what ends up happening, what we should be able to observe in the gravitational wave radial velocity spectrum is something like what you see there in that bottom right figure, which is that you still have the peak is at the gravitational wave frequency, but now encoded in the sidebands, you get this message frequency, which is plus or minus integer values of the exoplanet's orbital frequency. This is actually functionally, if you're familiar, this is functionally analogous to how FM, or frequency modulated radio, works. This is the type of spectrum that we get with FM radio. Okay, so while these two techniques physically, the underlying physics is the same, how that manifests and how the mathematics looks is actually a bit different. Now, for what we were curious to do, our group, was we wanted to say, okay, well, if this is a double white dwarf system, if we can detect it with this gravitational radial velocity, then could we also observe this electromagnetically and have some kind of complementary detection method? And while certainly you saw on that first slide, there are a number of different techniques that we could definitely explore in the future. Many of those are very highly tuned and work best when looking at main sequence type stars and their planets. White dwarfs are finicky because they're very small, they're very dim, and you end up with a lot of additional complications when trying to apply those techniques. But the one that we were most curious to explore, which hasn't been explored to date in the context of the LISA problem, is infrared excess. Now, if you haven't heard of this detection technique, I'll explain it in a moment. Personally, I hadn't heard of it, and I wasn't familiar with it until I started with this project. But we envisioned that we might be able to make complementary observations with JWST of these particular systems using this method. And I'll go into it in a moment. As we continue through the project, we also decided to throw in a third technique as a second EM-based one as sort of a backup or a complementary one just to see how well this one might work as well. And so I'll talk a little bit about astrometry. Envisioning, we specifically looked at what the Habitable Worlds Observatory might be capable of given their specifications in their mission design at the moment. So to begin as the starting point for the simulations for all three of these, we wanted to have somewhat of a realistic starting point. So we decided to just look at the currently known LISA binaries and select one of them to be our representative system. We picked this one, J2243. So for most of the simulations that I'll show, this is the values of the masses and the sizes of those stars is what we were using. We did change the distance to the system for our simulations to make it more amenable for the EM observations. As you'll see in a moment. But for the gravitational wave analysis, oftentimes, of course, we like to be able to calculate a signal-to-noise ratio quantity anytime we're talking about signals and trying to quantify how strong they will be. An important lesson that we learned, however, is that technically, adding an exoplanet to your system doesn't actually change the total signal-to-noise ratio of the system. Might be a little counterintuitive, but the reason why you can think about is that essentially what the exoplanet is doing is it's just siphoning power out of that gravitational wave carrier frequency and then redistributing it into the sidebands. So the total power doesn't actually change, it's just how that power is distributed throughout the spectrum is what's changing. So the total SNR remains the same. So instead, what we focused on as our just sort of our metric to study in this preliminary study was this residual SNR, which we quantify as the difference between the model that has the exoplanet versus the model that doesn't have the exoplanet. So the greater that residual, the more different these and more discrepant these two models become. And interestingly, what we see here in this particular plot, the discovery space of planet mass versus planet period, is that it tends to preference towards high mass, longer period exoplanets for the gravitational wave technique. Okay, so this sort of formed one of our points for study for the gravitational wave side. Then we wanted to look at the infrared excess. So the way this technique works is actually pretty simple. You pick your star you want to observe, you model how much infrared light you would expect to come from just that star, and then you make the observation. If you find that there's a lot more infrared light coming off of that body than you would expect from the star alone, that can indicate that there might be some hidden object in that system that you're just not seeing that is also emitting infrared, like a planet. Now what's really cool about this particular method, why we wanted to explore it, is because, like I said, most of the previous techniques are tuned for main sequence type stars. This method to date has been specifically used to search for exoplanets orbiting white dwarfs, and has been successful in that it has found several candidates to date around isolated white dwarfs, and it's even confirmed one recently. And I throw it up here because to me this thing is so bizarre. I love it. Nature gives us weird things. It's a binary M-dwarf system with a circumbinary white dwarf orbiting around it, and the white dwarf has a Jupiter mass-sized planet orbiting around just it. And this is the infrared excess data that was taken for this technique that helped to confirm this system, and you can see that at the higher wavelengths in the infrared, around 12 to 20 micrometers, suddenly you get a high deviation between like 10 and 20% more infrared light coming off of that white dwarf than you would expect from just the star by itself, indicating that possible planet. And so this is what helped to confirm this particular exoplanet. So we set out to ask then, all right, let's just see, can we apply this to systems that have 2 white dwarfs instead of 1 white dwarf? We used, again, J2243, our fiducial system. We modeled, given the sizes of those white dwarfs and their masses, how much infrared light we would expect coming from both of them. Combined, which is that top line. Then we modeled what a 7 Jupiter mass exoplanet would look like giving off infrared in the system there as well, so that's the blue line. And we can use this information then to calculate what the theoretical infrared excess would be for this simulated source. Now, importantly, I'll guide your eye to the 2 gray regimes. This is the optimal detection band on JWST for its MIRI instrument. It corresponds to the same wavelengths on both plots, that just the scales are slightly different. So this is where we're most sensitive with JWST, and importantly for this simulation, you can see that that blue line crosses the 3 sigma all the way up to the 5 sigma line within that detection band. So if this were a real system, this would be a very confident detection using this method. So kind of proof of principle that this might be applicable in the future. Now, like I said, we also wanted to consider sort of an alternative method to IR excess, and we focused on astrometry. There again, you're also looking for the wobble of a star due to the presence of a planet, but this time you're actually measuring the physical movement of that star over time with reference to very distant background and relatively stationary stars to figure out that movement. The work that we adapted was we looked at a recent study that was predicting the capabilities for the Habitable Worlds Observatory, and we just changed and sort of adapted what their work was for the systems they were considering to our double white dwarf systems, and to understand how that might look. And here's going to be the final, all 3 of them side by side, so you can kind of see what that discovery space looks like for this simulated source. Again, this is sort of the discovery space that we might expect for the LISA system. When we add in infrared excess, you can see that there's no technical dependence on the period of the exoplanet for the IR excess technique, so that we can reach out to very long orbital periods, but where the 2 techniques could observe the same system is where you get that 7 Jupiter masses or higher for this particular case. Now, a bit to our surprise, or at least to my surprise, when we threw in the HWO results, we found that HWO matched, given their specifications, matched quite closely to the sensitivity that we were getting for LISA. But the heavy caveat I would throw out here that's not captured in the figure by itself is that the technique, astrometry, would be very time expensive and require a lot of observations. So while it certainly might be doable and it would be interesting to explore, especially now that HWO is still in its design phase, it might not necessarily be the preferred method. We think that the IR excess, one of the major benefits of that technique specifically, is that it doesn't require very many observations to still get a confident detection of an exoplanet, if one exists. So this is kind of that preliminary work that we've looked at and the results of that. And I would say that if you're interested in this topic in general and are curious to get involved, you can certainly take a look. The Astrophysics Working Group has recently created a new subgroup focused on this particular topic of LISA triples and circumbinary planets, CBPs. So go there if you're curious to get involved or learn more. And if you want to scan that QR code, that will take you all to the references that I mentioned here in this talk. And with that, I'll take any questions.
Please use the standing microphone.
So in terms of the astrometry missions exactly, so go back to that slide where you have Gaia on there.
Oh, yeah.
I was wondering what can Gaia do for you?
Perfect. That was one of my backup slides. Yeah, so we also did throw Gaia in the study. Gaia was treated a bit more simply because we just kind of referenced that in this, again, this particular study that was looking at the habitable worlds, they estimated that the Gaia data release 4 was going to be expected to have about 300 times poorer precision than what they were estimating. So we kind of just focused on adapting their equation to get the HWO1 and then took 300 times for what, again, that's kind of just an estimate.
Before your very final slide, I had a really interesting sort of...
This one?
No, the one pointing you to triples, because I was thinking, okay, so the same argument applies if the white dwarfs are in a triple system, and some fraction of your 10,000 are going to be in some triple or even quadruple system.
Sure.
And so you should have the same effect, and you should be able to put constraints on the probability that these systems are triples. And you can scale it up to supermassive black holes with IMBHs around them, you know, in, for example, Bayesian disks, right? You might have an IMBH lurking further out, and so the Barry center of the system wobbles. You may get some interesting sort of signatures there as well.
Yeah, absolutely.
Yep.
Yeah, so yeah, I focused on exoplanets because that's the hot topic oftentimes is talking about planets, but certainly, as you mentioned, we could envision, and it might be more likely getting, like you said, triples with another small star or like a failed brown dwarf or something like that.
Yeah. And, well, what's also interesting about brown dwarfs as tertiary companions, right? If they have G modes, then if you've got a monochromatic gravitational wave source, it will do work on the G modes if it resonates. And so you'll get excess heating in these systems if they're resonating, so there may be an EM counterpart to the...
That sounds great. You should join the Astro working group on this and throw your ideas around. I love it. Thank you.
All right, I'm really confused. So some of us, including Valeria, who's back there, we wrote some papers on triples, including planets around binary white dwarfs. And unless I'm misunderstanding your plots, and you had an earlier one, it seems like what you're finding was the exact opposite. Like if you go back to that detection, that one, I mean, you're saying that long orbital periods of the external one are more detectable.
Yeah, you spotted the weird thing about.
I mean, it's the exact opposite. I mean, we've got
It is.
proofs in the paper, and we actually did MCMCs and verified it. It's the exact opposite as your result, so I'm completely confused.
Oh, okay. Well, maybe we can take this offline too. But this was a result that was very different from the EM observation, because normally, like you were mentioning, EM RV preferences the short period.
Well, that's what
And it
we
makes
found.
sense.
I mean, we've got like 3 or 4 papers on this, and hopefully not all wrong, but we even have analytic calculations that show. I'm just super confused now, because that's exactly the opposite from what we found.
That's totally fair. We can talk about more offline maybe, because it feels like a long.
And we also found that we were more sensitive to high masses, and yours seemed.
No, this one's still high.
That one, at least you go that way, yeah. But on the period, you're the exact opposite of what we found. But
All right, we've hit time for questions, so let's thank our speaker one more time. All right, our next speaker is going to be Rondeel, who is going to be talking to us about astrophysical population inference in the Erebor global fit.
Thank you, Alexander, for the introduction. Yes, I'm Koen Rondeel. I'm a first-year PhD student at the Observatory in Nice. And today I'll be talking about population inference of the galactic binaries within the Erebor. Okay, so first, a slight introduction on galactic binaries. I assume that you've all seen this plot before. Basically, it shows all of the galactic binaries that we could possibly detect within 4 years of observation time. So the entire Milky Way galaxy will contain roughly like 10 million galactic binaries, and only a fraction of that, like around 0.1%, of these binaries will be resolvable. So that ranges from 6,000 to 60,000 galactic binaries, depending on which astrophysical model is your favorite. And the largest fraction of these galactic binaries will form the galactic foreground, which you see in the blue line there, which causes the bump in the sensitivity. However, we will observe so many systems that it becomes interesting to actually do population inference on them. So, what is current status of the population inference for LISA? So, when I started my PhD 9 months ago, this was the status. There were 2 papers that discussed the recovery of astrophysics using like high frequency galactic binaries or assuming a some SNR threshold. And there was 1 paper that discussed a simulation-based inference method, which is a machine learning method to completely bypass the global fit and learn the sum need statistics of the population, which are very close to the hyperparameters that you use in population synthesis models. And then over the last few months, these 2 papers have been published. So the first one is from Alexander Tubiana and Jonathan Gare. They discuss a framework for LISA population inference, and the other one is from Alexander Criswell and collaborators. And they have also published a paper about population inference within the LISA global fit. So there are 2 more projects going around in the world. One of them is mine, and the other one is from Arianna Rancini at ETH. And we all try to do population inference, but we don't have our a specific session, so we're all scattered around the week. So I'm giving my talk, of course, now, and then Alexander Criswell will give it Friday afternoon, Arianna Rancini on Tuesday afternoon, and then Jonathan Gare will give his talk on Thursday afternoon. So,
you're populating the schedule.
Yes, exactly. So, why population inference for LISA, and why is it so difficult? So, first, let's take a step back to what's done for the LVK case. Here, they have interdependent events, which I mean that they only have one specific signal within a given time frame. They also have one single source type. They only have the binary black holes. They are prone to selection effects because the detector has a detection horizon and we cannot really observe beyond this. And there are no dominant stochastic backgrounds. So even while they search for one, since it's below the detection threshold, they can ignore it within a population inference. And for LISA, all this falls apart. So we have overlapping signals, both in the time domain and the frequency domain. We have multiple source types. So we have, for example, the global fit that we have to do, where we have to analyze the MBHBs, MRIs, galactic binaries, and even within the population of the galactic binaries, you have subpopulations of binary neutron stars, binary black holes, and combination of the stellar remnants. And the second one is that we will observe a complete population of galactic binaries, and I highlight here it's above a certain frequency. So above a certain frequency of LISA, you observe the entire galaxy that of galactic binaries that are emitting above that frequency. And there will be at least one stochastic component, which is the galactic foreground, which is something new that we have to do, because here that foreground is caused by the same population that we're trying to analyze. So what I'm trying to do is analyze this posterior. So we have, we're analyzing the posterior on the model, the number of galactic binaries, the parameters of the galactic binaries, the stochastic parameters given a certain data set. So this is proportional to the likelihood, a prior on your galactic foreground given the model, your prior on your model. There is a Poisson prior in there because we're this affects the number of expected to be resolved galactic binaries. We have our usual population prior, and there's a resolvability factor in there. And this resolvability factor can be sometimes a very vague thing. It can be an analytical function that we fix beforehand. It can be something non-parametric, that, for example, what Alexander Criswell has done. And preferably you would do this and fit this within a global fit, but currently we're not doing that yet. So to summarize, what we have to do differently for LISA is that for the LVK, they first analyze the single events, create the posteriors, then do the population inference using those posteriors, and do prior reweighting afterwards. For LISA, this will not really work because all of the sources will be correlated with each other, and changing changing the posteriors using prior weighting for one single source will affect the residuals and therefore can also impact other sources as well. So, the goal of population inference, there are three main methods. There's a non-parametric way, there's a empirical modeling way, and then astrophysical inference. So the first two are shown in this plot right here. This is the famous result for the merge rate of binary black holes as a function of the primary mass. And here we can see the empirical modeling, which is the spine model, where they leave the spine to be completely free in the parameter space, and then fit them to the data set they have. And the other one is a bit more constrained, where they assume there's a broken power law plus 2 peaks. And what I try to do is to completely ignore that and then do the astrophysical inference, which is basically try to infer your astrophysical hyperparameters that you choose or set within your binary evolutionary based synthesis codes, and then let your data tell you what we can actually constrain. So using realistic data and the full global fit, what astrophysics can LISA constrain, assuming sufficient knowledge on the astrophysical models. So I'm not doing the simplifications on the data and the data side, I'm doing the full global fit. But I'm putting a lot of constraints on the astrophysical models. For example, assuming we have perfect knowledge on all astrophysical parameters except one, and then varying that one parameter to see how sensitive LISA is to the change in that parameter. So, because we know what our astrophysical models will be, we can preprocess them. So here we simulate two populations, and we want to obtain the population prior, the population-informed proposals, and a prior on the galactic foreground parameters. To emulate all of these, we're using a normalizing flow, and to get from the populations to the population prior, it's basically putting this through that acts as a density estimator, and you use that as your proposal and your prior within your global, not as your proposals, but as your prior within the global fit. Then, because you do not want to propose low SNR sources within the global fit, you put a low SNR threshold, such that you're proposing sources that are more likely to be within the resolved population. And for the galactic foreground prior, we do something different. We use an iterative subtraction algorithm. This algorithm emulates the best case scenario of a global fit. And then you get out the expected population of resolved galactic binaries and an estimate on your PSD. This estimate of your galactic foreground we use in the global fit to estimate the posterior of the galactic foreground, run that through the normalizing flow, and we obtain a galactic foreground prior. And the method that we here use, so within the global fit wheel, we first try to update our stochastic parameters, then the galactic binary, and then we do our population inference step. So if we initialize a grid like this, we can see that, and we can hope, that your population inference within the global fit eventually converges up into one model. And what this actually emulates is that we have you're building up the evidence for one model, and you can compute the base factor for that, and that eventually converges to one number, and that tells you how well LISA can tell apart the two populations. However, for all of this, you need a global fit that runs. So we have been doing a lot of preparations. I'm part of the Erebor collaboration. I'm responsible for the galactic binary block there, and we are preparing for the LISA Mojito Data Challenge. And these are all the things that we are currently improving. Some have already been done, some are currently in progress. But a good thing to say here is that Mojito Run 1 is currently ongoing. That's for 9 months of data, frequency domain analysis, MBHBs, galactic binaries and noise. We already did a run without MBHBs, and that gave these posteriors. So here we see that there is a slight bias within the noise parameters in the top right figure. However, this is to be expected because we're doing it a frequency domain on a non-stationary data set, so you would expect a bias there. If you want to know more about the time frequency analysis that we do for the Erebor Global Fit, you can visit Alessandro Zottini's poster at one of the poster sessions. And if you want to know more about the Global Fit in general, Thijs van Dittenburg will give a talk tomorrow, on Wednesday morning. So I was hoping to show you a plot like this. It basically is a base factor surface comparing different astrophysical models together. But unfortunately, the global fit started working 2 weeks ago, so I have one comparing these two models. So I will not go into this, the details of the two populations, but what we're modeling is the effect of the tidal effects within the evolution of the galactic binaries, which will result into a different number of resolved galactic binaries that are either that have a positive f dot or a negative f dot. And what you get out is a base factor that is pretty high. However, this is very, very preliminary still. I'm still checking a couple of things, but this does seem quite good. However, since we're in a simplified scenario, we cannot really say that if we have a high base factor, that you can distinguish them both. The only thing that we really can say, if we get a low base factor, we can definitely not. So, there are multiple caveats on the interpretation of these base factors. However, the degeneracies between astrophysical models is something that we definitely look forward to modeling using our analysis. For example, consider a population model that predicts twice as low galactic binaries that you expect. That can be compensated with a twice as high stellar mass of the Milky Way. So therefore, there's a degeneracy between the two. You cannot really separate them. And then also, there's a degeneracy between the different simulation codes. And if you're interested in that, that's the task of the UCB Catalogs project. And they are publishing the results very soon. Then I will end with this. I've built an extendable framework for population inference within global fit. We're exploring what astrophysics LISA will or will not be able to constrain. The next steps are to run many global fits, which will take maybe a lot of time, and complete the full base factor surface for one parameter. And then we want to perform different model checks, of course. And I'll end with this slide. So great thanks to all of my collaborators, and thank you all for your time.
All right, we have time for a few questions. Got some coming forward. You know the drill at this point.
Hey, thanks, great talk. So I do foreground calculations for the UCB catalog project, and we have 100 different foregrounds and 70 analytical fields. If you want to see them, come see my poster.
Yes.
Vladimir Strokov.
Definitely look forward to those results and those catalogs.
Let's say again.
I definitely look forward to all of having those catalogs available.
Hey, Kun, this is fantastic. So I have a really general populations question, spurred maybe by knowing the Mojito catalog a little bit too well. How diverse should we think that this population will be? And do we think we will have a good model, even just a sort of generic model for the population, or should we be as agnostic as possible, for example, similarly to the LBK approach?
Yeah, so personally, I don't really know that yet. I think there are a lot of degeneracies between the parameters that we use to simulate the populations. So it's quite difficult. That's also why I want to do this and see what we can actually tell apart. Maybe the eventual conclusion will be that we can only do empirical fits, but I'm afraid that maybe we will end up at a similar stage as the LVK is, where we want to explain a certain peak in the like merge rate distribution and try to explain with many models, but are not really convergent onto one. I hope that answers your question.
Partially, but I think we have hopefully 10, 15 years to.
Hopefully.
Thanks.
Anyone else? I will very happily take chair's prerogative. Somewhat related to Ariana's question, the one thing that every population synthesis person I talk to is confident on is that all of our pop synth codes are wrong. Hopefully they're also useful, right?
Yes.
How do you envision, right, it's 10, 15 years from now, how do you envision actually implementing this kind of Uber model comparison approach? Do you also throw a non-parametric model in the mix? what can we do?
So I think it will be very difficult to do full population inference within the global fit. Like you know that it's very difficult if you do like the inference, you actually get it to converge. That being said, I see a future forward where most of the heavy lifting of getting a good parameter point to start from is done by machine learning. And from there, we will actually try to do our Bayesian analysis and see what we can actually learn.
Let's thank our speaker one more time. All right, our next speaker is going to be Manuel Barrientos, and he's going to be talking to us about precise parameters for 2 LISA sources.
Oh my God. This thing is already spoiling all the presentation.
Oh, no.
All right. Well, good afternoon, everybody. My name is Manuel Barrientos. I'm a PhD student at the University of Oklahoma, and today we're going to be talking about this paper called Precise Parameters for 2 LISA sources. If you want to follow the presentation in detail, you can scan the QR code. It will take you to the paper, and if you don't want to do that, you just can listen to this presentation for the next 11 minutes, I guess. And as you already saw, well, this plot has been frequently shown throughout this day, I guess, and what I want to focus today is not only in the all these LISA sources, but I just want to emphasize a new method that can help us improve the characterization of these systems that is like less or different than what we usually do. We know that this double white dwarf of binaries will be the dominant galactic population that LISA will be observing. And these are beautiful targets because we can do multi-messenger astronomy, as we all know. But however, if we want to put these targets or these sources in this plot, we have to be able to constrain the parameters electromagnetically, in particular masses, inclinations, distances. And you will ask yourself, how do we obtain those electromagnetic constraints in the first place? And what we usually do is something like this. You will go to a telescope, you will put a filter on, and you will observe your favorite binary system out there and see how the light of the star or the system will change in time. This is what we call a light curve. And the light curve is very incredible because it will tell you information about the geometry of the system. And this is the case of system J0651. This is a 30-minute period system. And as you can see, the data looks very clean. When you try to model this type of system, there's no too many issues. You can constrain masses of both components, like here, 0.51, 0.27, and the inclination of the system at 87 degrees. So this looks great. And in paper, you will think that all the system will look like this. When the reality is that, no, actually, like most of the cases will look like this. This is system J2322, and this is going to be the main character of this presentation, so please remember the name. This is a 20-minute period system. And as you can see here, we don't see no clear modulation, no tidal injections. So what information can we get from the light curve? There might be an indication of a low inclination system, but as I'm going to show you now, for example, this is one of the solutions that I found when I was trying to model only the light curve, and I will get parameters that are not consistent with a white dwarf. Like you can see masses of 3 and 3.37, 1.03, that's not that off. But if you cheat a little bit and use other way to characterize the systems, you might be able to find other set of solutions that might be consistent, and they will tell you maybe how the light curve should look like if we could get this type of information. So this is just to motivate the fact that there's still a lot of work to be done when it comes to characterizing the systems electromagnetically that LISA will be observing. Now, when it comes to parameters, inclination might be the most important one. However, surprisingly, almost 54% of the systems that we have studied and known have unconstrained inclinations. So how do we deal with this type of problem? So this is also another motivation that we have to add or look for additional observational approaches. to model the systems. So the two main questions that I want to answer in this, or like I just want to like put it out here and maybe discuss and talk and show you what I have done, is that how do we characterize the LISA binaries when optical constraints are weak or degenerate? And the second question will be, how do uncertainties in these electromagnetic constraints affect LISA pipeline's parameter recovery? So to start, again, J2322, our favorite system. When we do this type of modeling, it's kind of tricky because you observe the systems and they look like they are single line binaries. You cannot really see two lines, as we can see here, a snapshot of how the spectroscopic observations of the system look like. You see the boundary lines and the fit. So what we do usually is a joint fit. You use not only the spectroscopic information, you use photometry, you use distances. And when you combine all these three things, you will get some type of solution. In this case, the best solution favors a really hot white dwarf, or around 19,000 Kelvin, and the solution also favors almost equal mass components for the system and an inclination of 27 degrees. And at the same time, when we do this type of analysis, we can quantify the contamination of the unseen member. In this case, it was around 15%. So parameters for the hot member are not inferred directly. We are trying to get them doing a decomposition of the optical light that we get. So this is kind of an issue. So now, this is when our method comes in, and it's very cool because in this case, what we did was, okay, let's test the optical solution. Is the optical solution correct or not? And for this, we applied for time at with HST, and we got UV spectra for J2322. This is how the spectra looks like. You just see the Lyman alpha line. And the good thing here is that since we have a very hot object, we are able to isolate the flux of the hot object, in this case, and anchor the solution for the primary companion, in this case. For the distance over there, we find, in this case, the best fit gave us around 20,000 Kelvin white dwarf with 0.31 solar masses. So once we have that solution anchored, we can go ahead and redo the joint analysis and find the properties for the secondary member, in this case, at 1900 Kelvin cooler companion. And as you can see here, I had in red tag, like the old set of parameters that were proposed in the previous paper, and then my new set of parameters, and you will say, oh, they actually look exactly the same. Like, what's the real improvement here? Well, and it seems like in some cases we will run into this type of situation where you don't really like change the optical solution because the optical solution was good. But what we did here is that we actually independently measure the properties of the hot white dwarf and independently validate the optical solution, which is valuable. So now we have the secondary character of this presentation is J0634. Again, another pretty light curve with no real modulation, no real constraints from there. This is a 26-minute period system. And what's interesting about this system in particular is that when we do the joint analysis, we find that the Gaia distance, which comes from parallax, and the distance that comes from spectroscopic measurements don't really match. They differ by almost 130 parsec. So this is a clear indication that the joint analysis that we did has a clear contamination that is more prevalent than the previous case. So the solution here is actually good. When we do the full joint analysis, the solution favors a 27,000 Kelvin as a hot white dwarf companion. The other one will be a 10,000 Kelvin white dwarf. However, we have multiple sets of solutions that match the information that we have both spectroscopically and photometrically. And this plot over here for log G2 versus log G1 kind of illustrates this degeneracy. In a short parameter space, what I want to emphasize here is that for different sets of solutions, your temperature one can oscillate between 31,000 Kelvin and 24,000 Kelvin, and your mass can go from 0.39 to 0.52. So in a very short parameter space, you can get multiple solutions that differ. So this might be an ideal case, for example, where the UV spectra can break this degeneracy and help us constrain the system better. So now when it comes to the gravitational wave simulation that you might all love, better than what I just showed, what we do here, we use glass pipeline, and in particular the BGVM CMC sampler that help us go from this set of electromagnetic priors, in particular masses, inclination, distances, frequencies as well, to the output set. In particular, we will focus on the gravitational wave amplitude. What we see in this case is something interesting. When you run glass, you can have the choice, you have the choice to use EM priors or use the uncertainties for the inclination. So we wanted to see how this affect the signal that we will get from these sources. So what we realized is that for J2322 on the left side and J0634 on the right side, we will increase the signal that we can obtain at early stages for, by LISA by a factor of 2, and then this increment is larger for a full LISA mission, 4 years. We go from 4 on J2322 and 3 for J0634. So definitely the uncertainties for these parameters can be very relevant, and in the future we also want to like investigate how distance, for example, where the uncertainties in distance are very large, how those also affect the signal that we can get. So for the sake of time, I will leave you with my conclusions. Takeaways, main takeaway, UV spectroscopy can be a really good way to get parameters or improve parameters for these systems when we don't have any other way to do it with optical data. Uncertainties will be relevant when it comes to recovering signal from these sources. And for future where we have more systems that can be candidates for this type of science. So with that, I will take questions and thank you.
Super interesting talk. I was curious, this UV spectroscopy sounds really interesting. Have you looked at, so of the number of systems that have the unconstrained inclination, how many, HST could actually resolve or, for this kind of thing?
Yes, that's a good question. Out of all the systems there, I haven't analyzed one by one just yet, but I'm currently working with the ELM survey, which is extremely low mass survey. It's a survey run by Warren Brown and McGrath Killick, and we have a bunch of sources. In particular, we have around 20 systems there, and those are not necessarily in the 41 that were shown in this Thomas Cooper paper, but I'm pretty sure we have at least in the tens sources that can be done with HST. However, doing it is a little bit expensive, and we will see. We got the time for 22. We will see if we get time for years J0634. That will require around 1+ hours. So that's 2 orbits on HST. So we will see. I will say that that's the minimum that you will get for any of these sources.
Thank you.
Any other questions? We have some time.
The improvement that you get in for that specific system, is it because of the priors, or is it because the signal becomes intrinsically stronger, given the inclination is different and the distances? They're different things, right? And
yes, I think it's a little bit of both. I mean, since it's a low inclination system, we'll have a larger signal, or the gravitational wave signal will be larger for that system. But I feel the fact that we were able to constrain the parameter space in the simulation, I think that also increased the signal that we can obtain. Mm-hmm.
I have a boring question. What are the error bars that you're showing here? 1 sigma, 2 sigma.
1 sigma, 90%.
Oh yeah. Wait. In which case? Oh, the error bars I have it throughout the presentation. They are all 1 sigma.
Okay.
Yeah, all 1 sigma. Sorry.
Cool.
Oh.
Cool. Let's thank our speaker one more time.
All right. Yeah, my talk's a little bit out of place in this session. It's my fault. don't blame the scientific organizing committee, even though I'm on the scientific organizing committee. We did mean to mix up the talks, but the reason mine's in this session is I have to take a flight at lunchtime on Friday, and my talk was scheduled after my flight, so I switched with someone who couldn't be in this session. Anyway, this is relevant to all LISA analysis, so I guess it's not out of place in any session, but just telling you about the shift we've been making to time frequency analysis. So why do that? You know, it's just an orthogonal transformation on the data, so it doesn't change the information. So it has exactly the same information as the time domain or the frequency domain, so it's not adding anything new, but it's packaged in a different way that's sometimes a lot more informative. It's also a natural way to model things such as non-stationary noise, and it also allows for sparse and very fast likelihood evaluations. Also has advantages for modeling things like data gaps, because they're sort of isolated in time, and glitches, which are these short duration things we might have as well. So, I mean, there's a long history of using time frequency methods in gravitational wave analysis. It's done in LIGO. I think the first algorithm that I know that introduced it and used it in gravitational waves extensively was coherent wave bursts, so their likelihood is using the same WDM waveform basis that we've now switched the glass analysis to. So, what's going on? You're just trying to get rid of the thingy? Doesn't matter. Okay, so here is an animation I made some time ago. That's the LISA antenna pattern. The red areas are where it's most sensitive. And it's a bit like watching a lava lamp, really. But you notice that you can see the galaxy in the background there, shadowy galaxy. There are times of the year where the red blob goes right over the center of the galaxy, and then there's another part of the year, 6 months out, where the other blob goes over and kind of clips the edge of the galaxy, right? So you get two peaks, one slightly higher than the other, because one time it's going right over the center of the galaxy. Okay, well that's thunder and lightning sound effects. Okay, so you can see that then in this modulation pattern. So you've got power at harmonics of a year, 6 months, 3 months, whatever. And depending on the shape of the galaxy, it modifies the modulation. One of my students, Sudi, worked on making these calculations about how the different interferometry channels are modulated. Well, that then means that even if we just had perfectly stationary instrument noise, the confusion noise is going to be non-stationary because of this modulation, right? So in the frequency domain, what that does, I did this calculation a few weeks ago. I couldn't find it published anywhere. It's the noise correlation matrix in the frequency domain for non-stationary noise. I don't know if it's a new result. Can't be. It's too simple, right? Just too obvious a thing. But I couldn't find it anywhere in literature, but I derived it for myself so I'd understand it. Anyway, this little s thing is the Fourier transform of the square root of the dynamic spectrum. The power spectrum is a function of time, right? So that's what the noise correlation. It's a Hermitian matrix. If the noise was stationary, then you just get the usual diagonal noise correlation matrix. That's why we've typically done analyses in the frequency domain in gravitational waves, because you get a diagonal noise correlation matrix, and that's very cheap to invert and very cheap to calculate likelihoods. The trouble is, when it's non-stationary, it becomes a non-diagonal Hermitian matrix, right? Then the Hermitian nature is important. The complex parts tell you when the noise is happening. So if you actually take the galactic confusion noise, these are all new results, you're the first people to see them. If you take the galactic confusion noise and you calculate it in the Fourier domain, that's what the noise correlation matrix looks like, that's what its inverse looks like, and when you then calculate the cost of using this likelihood, this is 36 times more expensive than if you could do it with a diagonal covariance matrix, right? So computational cost goes up a bit, but here this modulation is slow, it's happening on sort of year timescales. As I mentioned, if you calculate the signal to noise of a short duration signal, using the full noise covariance matrix rather than the diagonal approximation that everyone's been using up until now. This is what you get with the diagonal approximation. This is the signal to noise as a function of time if you use the non-diagonal noise covariance matrix, and it's the complex off-diagonal terms that give you that variation. And it's a variation of a factor of 2 in signal to noise, right? It's pretty significant. Matthew Digman and I wrote a paper on this years ago, a few years ago now, showing similar things using wavelet domain analysis, but this was actually just done in the Fourier domain. Okay, what's interesting, if you look at a year-long observation of a galactic binary, these are the posteriors done, calculated using the diagonal frequency domain likelihood, and the ones using the WDM wavelet representation. So here's the wavelet transform of a galactic binary, and there's the frequency domain transform of a galactic binary in power. You get essentially identical posteriors, and that is because it doesn't actually matter with a continuous signal that barely varies. It doesn't matter, it averages out over a year and you get the same result. Now, you'd get a different result if you only do it for 3 months, right? Or a shorter time. But if you do it for a year, you get exactly the same result. But it makes a big difference for short duration signals like black holes. I wanted to show you a plot of that, but Tyson said the code's broken right now. So we're doing a lot of changes, and so we put all the wavelet transform stuff in, and apparently the whole thing's not wired back together again yet. So it's in parts on the floor getting rebuilt. So anyway, if you have a shorter duration bump, like about a week-long rise and decay of like a little perturbation in the noise, then it gets way more spread, and now your likelihoods in the Fourier domain would cost 100 times more to calculate, right? So once the non-stationarity becomes more rapid, it becomes very expensive to continue using the Fourier domain. In the wavelet domain, it naturally can model the non-stationary noise. The wavelet domain noise correlation matrix is almost exactly, we can make it almost exactly diagonal. So it's very cheap to evaluate. And the other nice thing is that a signal, when you go into the wavelet domain, you have basically roughly the same number of pixels in time as you have in frequency. So a line in that space has length root n, where n is the total number of data points. So a single harmonic signal has root n points. So your cost of your likelihood goes down to root n instead of n. Right? So it's a natural heterodyning without even having to heterodyne. You can use different discrete wavelet transforms. The one that we've been using up until now is that purple one, the Maya window, which is very nice and compact, like a top hat in frequency, but that means it has bigger lobes in time. At the LISA sprint that I hosted this year in Bozeman, one of the teams, we implemented this Gaussian window, which is an alternative window, and it's more compact in both time and frequency. And, you know, there's pros and cons between different representations, but this one, you can use whatever. They're both orthogonal. It leaks a little bit less at gaps, which is the reason that we wanted to look at it. So you can see on the right, when you have a gap and there's a signal there, a galactic binary going across, there's significantly less leakage with the Gaussian window than there is with the Maya window. But don't worry about leakage and gaps, because we have a solution to that as well, and that is we use Bayesian data imputation. If you go to parallel 3A on Tuesday at 2 o'clock, one of my students, Noah Pearson, will be talking about Bayesian imputation, and so here's a gap, and you can see it all sort of like blurting out, and they're filling it. Why was the stuff in there? I forget why there was so much stuff in that gap. No, it was just leakage, I guess. This was really strong noise. But anyway, with the imputation, we take away the edge effects, right? So we can fix the gaps. So don't worry too much about the gaps. And they're very naturally handled. There's matrix operations involved in this imputation, and they're nice and compact in the time-frequency domain. So it makes that a much cheaper prospect. We published a paper on this. You can read about it. You can also go and hear Noah give a talk about it on Tuesday. Okay. Another nice thing is that you can do very fast waveform calculations, like the waveform response. So here is a galactic binary, and here's just a little bit. This is just 500 seconds of data, and you can see the full signal there in purple, and then the green one has been heterodyned down by an integer number of, this is the frequency pixel size in the wavelet transform. And it turns out one of the nice things about these WD transformations is that they have translational invariance. The signal is the same if you move it by an even number of delta Fs in frequency, okay? So what we do is we move the signal down, and now it's very slow, so you can sample it on a very, very coarse grid, which means it's very cheap, and then you just you perform the transform at this frequency, almost 0, instead of at that frequency, and then you just shift the result up. And so to show you that zoomed in on the next panel, that is the signal calculated at full cadence. There's the signal calculated heterodyned, and you just shift it up. It's identical. So you just do the calculation at low frequency and then just shift it up to the frequency you want it at, and the cost is dramatically less, right? So now in glass, we use this method to calculate the galactic binaries, combine that with TDI on the fly, which is another fast technique for doing the instrument response, and our computational cost, even for like a 1 year or 2 year or 3 year galactic binary is at the millisecond level or less, right, per waveform. And that's without any fancy GPU stuff. You can do that on top of that. This is just the raw CPU thing, because the algorithm requires so few points, right? We've got algorithmic speed up, and then we can do what Michael Katz does and stick it on GPUs and make it even faster. The nice thing is it's really tiny as well, right? Because it's all downsampled, so it fits on a GPU, right? So it's going to be very natural to stick this onto GPUs. And just the last slide here, I've just got it going now on black holes with multiple harmonics and precession. And again, I've got this root n cost scaling. So for black hole mergers, even low mass black hole mergers, we're still talking millisecond times to calculate the waveforms and everything. So very, very fast. And yeah, so that's what we're doing with the time frequency analysis for LISA. Thank you.
Questions?
Thanks for the very nice talk. So in the time frequency analysis, you basically divided the whole data set into several shorter data segments, right? And in each data segment, you basically reduce the frequency resolution, right? So
no, we didn't divide it. I mean, it's the entire data set. It's just been transformed into a time frequency representation. We didn't break it up into chunks.
Okay, because in the literature, there are some data analysis method, for example, use the short Fourier transform.
Yeah, this is not that.
Okay.
Right.
So WDM
this is mathematically, it is a orthogonal transformation on the likelihood, right? So you apply an orthogonal transformation to the data, orthogonal transformation to the noise covariance matrix. It gives identical likelihoods. Identical. Okay. There's no approximation, right? It's exact. So there's no loss of information. It's just the same as a Fourier transform.
Okay.
Right? So it's just that's an orthogonal transformation described by a matrix. This is an orthogonal transformation described by a matrix. It's exactly the same. There's no loss of information, has exactly the same information. It's just that, why do we use the frequency domain in LIGO analyses? Well, we assume the data is stationary. Not quite, but it's close enough. And so we can get away with the diagonal noise covariance matrix. And so the cost of the inverting it scales as n rather than n cubed, and the cost of the likelihood scales as n rather than n squared, and so that's why we do it in the frequency domain, right? in pulsar timing, we have to do it in the time domain, so we have these expensive n-cubed operations there. But yeah, if you do time frequency for non-stationary noise, it stays order n. Yeah.
Okay, thank you so much.
All right, we're at time, so if you have more questions for Neil, you can find him after. We're going to bring up our last speaker here. Our last speaker is going to be Alice Perego, who will tell us about finding Lisa white dwarf binaries with multiband photometry.
Thank you. Hi everyone, I'm Alice Perego. I'm a second year PhD student at the Observatoire de la Côte d'Azur in Nice with Astrid Lamberts and Nelson Criswell as supervisor. And today I will talk about how to enhance the multi-messenger science that we can do with LISA galactic binaries. In the Milky Way there are billions of white dwarfs, and we know that with LISA we expect to detect the ultra-compact binaries, around 10,000 single detections, while the majority of them will create a foreground signal. These are indeed ultra-compact binaries, so orbital periods lower than 1 hour. But in general, white dwarfs are also detectable by telescopes, especially the most nearby, the young systems and the low-mass systems. Indeed, we have a current sample of hundreds of thousands from the latest Gaia data release. The goal here is indeed to investigate the overlap between these two populations that you can see here in red. The primary goal is to extend the list of electromagnetic observations that we can obtain for this type of system, so for the expected sources detectable by LISA. Why we are so interested in these systems? Well, first of all, as you know, if we have a reliable set of well-characterized electromagnetic observation of LISA binaries, this can really validate the LISA performance. They can help LISA data analysis, reduce the global noise challenge, the overall noise that we will get in the LISA data analysis. And indeed, the current sample of verification binaries is around 30 systems. I'm only considering the detached double white dwarfs, so no interacting binaries. But in general, we can combine the gravitational wave and the electromagnetic informations, since these two methods provide different types of parameters and measurements. With EM data, we can improve the accuracy on the gravitational wave parameters. We can obtain the measurement of the component masses instead of only having the chirp mass. And most important, an EM counterpart is essential if we want to study tidal interactions, which is one of the LISA science objectives on binary evolutions. And so with that, we can study also the fate of the system and have insights on type 1a supernova progenitors. Finally, by extending the electromagnetic observation of white dwarf binaries, even if they are not resolvable specifically by LISA, this will help us to have a complete view of the population, so not only focusing on the high frequency one, and this can help us on refine the population's synthesis code that we use for LISA studies. How can we do that? Now, the ultra-compact double white dwarfs are a very tiny fraction of all the electromagnetic observations that we have for white dwarfs, because there are also single white dwarfs and white binaries at very large orbital periods. Now, these double white dwarf binaries at very short orbital periods instead, they had to undergo a very special evolutionary path, which is defined by very complex processes, like mass transfer and common envelope phases, and this leaves a clear imprint on the mass, on the age of the systems, and this is reflected also on the electromagnetic emissions that we expect from these systems. So, if we can study their EM signatures, we can find a way to distinguish this, let's say, most interesting for us type of system from the whole population of white dwarfs and white binaries, single white dwarfs and white binaries. Okay, so in order to do so, I started by creating an EM catalog. I started with a population of white dwarfs, both as single stars and in binaries, because they have the same photometric emissions. I combine a population synthesis code with a semi-analytical model for the Milky Way distribution and the age. Then, when white dwarfs are formed in a binary, in a single star, they just cool down. So I used some cooling models to have an idea of the temperature and the luminosity at the present time, and from that we can construct the photometric magnitudes. We are particularly interested in the U band because white dwarfs have a dominant emission in this filter. Now, the electromagnetic emission that we get from the star is actually altered by the dust that is present between us and the star. So this creates the extinction and the reddening phenomena, so we have to take this into account. Using three-dimensional interstellar dust maps of the Milky Way, and this clearly affects the detection efficiency of the telescope in the inner disk, as you can see in the image. And finally, to have a realistic simulated catalog of electromagnetic observation, we have to apply a sensitivity limit for the telescopes. And in this case, I'm using observed magnitude lower than 24.5, which is, let's say, a larger limit in respect to Gaia or LSST. But this can be achieved. This is achievable with future telescopes and surveys. Then we can study the results. So, as I said, we are interested in photometric observations. So we can construct color plots, which do not require a distance measurement from the electromagnetic side. We just need the color, so U minus G versus G minus R in this case, and we can study the density distribution of the catalog that I got. And I am here distinguishing between the double white dwarfs that emit inside the LISA band and the rest of the population, so the underlying population in blue, which is indeed the single star and very wide binaries. And we can see that the magenta area actually separates from the blue one, meaning that if we focus in the area that I have highlighted, the majority of the observation comes from double white dwarfs emitting in the LISA band, with a smaller contribution from, let's say, binaries at lower frequencies, so towards up to 10 to the minus 7, while very wide binaries and single white dwarfs emit mostly outside of that region, are found outside of that region. So we can exploit this by focusing in this area to actually do the follow-up, which is required to confirm the binarity of the system. And another important thing in this plot is that I also compared with the real data, so observation from Gaia and SDSS to get the photometric bands. And I quite well overlap with the simulated population that I constructed. Now, this method is driving a proposal for the Canada-France-Hawaii telescope, which is a 3.6-meter telescope located in Hawaii. It will conduct a community survey over a 6-year period just before LISA operation time, from 2027 to 2033, and it is actually offering between 400 to 700 nights. We just submitted the proposal at the end of April in collaboration with other 2 working packages, which focus on and are addressing different type of scientific fields, from the discovery of small solar system objects to active galactic nuclei. This is done because the main goal of this community survey is to provide the maximum scientific impact to the community. And this is why also they are offering such a large number of nights. With this survey, we want to do a photometric. We want to achieve a photometric survey of the galactic plane down to a magnitude of 24.5 in the U filter. Indeed, the Canada France Hawaii telescope has a very sensitive camera in this band, and this will actually give us a very valuable data set with calibrated photometry in new GNR, which has indeed a very high value not only for our scientific goals but for a wide variety of science fields on stellar and binary evolutions. Now, we expect with LISA to find around 10,000 of double white dwarf detections, and a fraction will be indeed the multi-messenger sources. There are efforts to expand the list of electromagnetic detections of the same type of systems. But we have to ask ourselves if we are able to correctly identify the overlap between these two populations. With LISA, we will get an indication of the sky localization, but within the sky localization, we expect multiple electromagnetic, other electromagnetic sources. So this prevents us to correctly find the right source and the multi-messenger source. Even if we only have one electromagnetic detection in the LISA sky localization, there is a high probability that is not the right source, because it's just a fainter system for LISA, which contributes to the galactic foreground, because but it's closer in distance, so it's detected by the telescope. So we really need more information to constrain the match and avoid the bad matches. The first choice would be the distance, but with Gaia and LST we will have parallaxes, but the parallax error can become very, very large for fainter sources, and this prevents us to constrain the match and so reduce the contamination. We can have from the EM side also the orbital period, but this is really expensive, so we have to understand what is the accuracies that we have to require in order to constrain the match and indeed avoid the mismatches. An alternative is to study the two populations separately, so account for the selection effect that we have from EM and from the gravitational wave side, and combine the two and study the whole population in the galaxy. So this is the last slide, the summary, and I will finish by saying that the first step to enable and enhance the multi-messenger science for LISA galactic binaries is doing very wide photometric surveys to get the majority, say, most fraction possible of photometric observations of white dwarfs. Then they can be pre-selected to find candidates for the follow-up and have an indication on the binarity. But the ultimate goal is really to fully characterize all these systems. This means measuring the component masses, the ages, all the orbital parameters, and understand the final stage of the binary itself. And this is a very ambitious goal, which has a lot of challenges, and the best strategy is still an open question. So if you are interested, you can reach out. Thank you very much for the attention.
All right, we have a time for a couple questions. Just letting you know that there's going to be an announcement from the organizing committee afterwards, so please stick around.
Hi, nice presentation. Could you go back to the plot where you show the follow-up, the blue color?
Sorry?
Before this one. One more? Yeah. So from the binaries that you predict to see, do you know what was the ratio of detached versus the ones that are actively mass transferring?
No, here I'm not considering mass transferring system.
Oh, okay.
I'm only considering detached white dwarfs.
Got you.
This is why the photometric emission, let's say, is similar and cannot really constrain the binary. Have an indication on the binarity because in most cases we only see the most luminous of the two. And we do not have any insight of the other, if there is a component or another one. The thing is that they separate quite well because of the properties like mass and age of white dwarfs that are found in ultra-compact binaries, because usually they have low masses because they had to undergo mass transfer to arrive at such short separations, and so they tend to be a little more in that area.
And I have a follow-up on another thing. You mentioned that there is a way of separating or focusing on the white dwarf binaries using the orbital period. Could you tell more about how you would do that?
Let's say this is all of this is, let's say, still working on. Yes, it's.
I just wanted to add that if anyone is interested, I'm presenting on that poster 1.1. That's it. Thank you.
Thank you.
That's going to be our time for today, so let's thank Alice one more time.